Good morning, everyone. Great to see you again for this last and I'm sure very interesting and stimulating part of this fantastic conference. Today's program, as you know, is a bit changed. So we will first listen to a keynote presentation. We will then break for coffee. After the coffee, we will reconvene for questions for the speaker, and then we will continue into the last part of the day, what we called yesterday Fråga Lund, Ask Lund, where some researchers will comment on questions that have been sent in by you, and of course, open discussion for everyone on all the questions. We will now hear about understanding the language learning brain with cyber-enabled approaches and computational methods. And talking to us about this, coming from the Center for Language Science at Penn State, USA, is the Professor of Psychology, Linguistics, and Information Sciences and Technology, Professor Ping Li. Welcome.
Thank you. Well, thank you, Lisa, and for inviting me, and thanks to all the members in the organizing committee. It's really a pleasure and honor for me to come here to discuss really interesting issues with you. I want to start by saying, actually, on the airplane coming here, I knew that I had come to Lund before, a long time ago. And after I got off the airplane, I put up my CV. I looked up Lund, and it brought me to the last page of my CV. And the only item on my CV on the last page was a conference presentation that I made in Lund, at Lund University here. In 1988, when I was a grad student, my first ever conference presentation was done here. And so in a way, Lund is a place where I, even though it's the last item on my CV, which means it pushed to the front pages of my academic resume. So it's a good place to be. And also yesterday we had a really interesting discussion about interdisciplinary research, and I hope by way of my talk you can see that I have embraced interdisciplinary approaches and perspectives in my career. So let me give you a quick outline of my talk today. I will provide a few general pieces of information on the background, some general framework. My focus today will be on second language learning, very different from some of the presentations earlier in the last 2 days. But I will make very clear connections between the approaches that I take with the previous talks and research approaches. I'm a psycholinguist. I'm really interested in individual differences in learning. And I thank the organizers for giving me some extra time so that I will actually have some demonstrations. But I will also try to illustrate the perspectives, approaches using neurocognitive, cyber-enabled, and computational methods. And finally, I give some future promises of these approaches. So, the general framework that I have embraced in my work, at least in the last decade, has been this so-called new sciences of learning, illustrated by three aspects. One is that learning is computational. Second is that learning is brain-based. And third is that learning is social interactive. All of these perspectives or these aspects are really clear to the audience sitting here. And this was very clearly illustrated also with the language learning. So in this article published in Science in 2009 by Andy Methoff and Patricia Kuhl and a few colleagues, they pointed out that human language acquisition sheds light on the interaction among computational learning, social facilitation of learning, and shared neural circuit of perception and production. So language learning is really a prima facie case for illustrating these aspects of learning. Now, my focus today will be really on, as I mentioned, on second language, but I think a second language equally points to these aspects. And I will also mention how we study technology and how technology actually drives the learning in my talk today. And finally, because of my background in doing computational models, I will illustrate with some data and models how those models and data might inform us of the important mechanisms in student learning in general. So that's basically the plan and the general framework with which I take in my work. So here's my lab. We have a very diverse group of people doing lots of different stuff, and our work has been mainly funded by the National Science Foundation. And the work in my lab takes multifaceted perspectives as well as multiple convergent approaches using functional imaging, functional MRI, EEG/ERP, computational models. And recently, we have also combined eye tracking with MRI. So for example, in the eye tracking and MRI combination studies, we actually put the subject in the scanner, have them read whole text, sentence by sentence, and there's a eye tracker in the back of the machine that can capture the eye movements of the subject while they are reading the text. By the way, you will see a lot of illustrations from my daughter, Jackie, who is a young artist, helped me to put some of the really complex pictures into sketches. So in the eye tracking case, we are able to capture simultaneous movements of eyes and the brain responses. So I have a title in my talk as cyber-enabled. So we at Penn State, we have this Penn State Institute for Cyber Science. So you ask, what is cyber science? It's research that requires ultra-fast computers and computing power and all massive storage, such as big data analytics, advanced simulation, machine learning, predictive modeling, and cyber-enabled tools and methods. You will see a little bit of this in my talk today, where we at least used cyber-enabled tools and models. We have built some predictive algorithms and models, but I won't really have time to discuss this today. We have used the machine learning methods to analyze our data, and we've done a lot of simulations. But I hope you get a feel from some of the very quick illustrations of these studies that I'm going to tell you a little bit about. So first of all, in my earlier career, I spent a lot of time doing computational simulation modeling. Colleagues and I build models such as this one that can take input as phonological forms and then build semantic representations and then output sequences of speech. And with these models, we actually are able to capture, for example, semantic representations in first and second language, separating animals by their type and their features. And with this type of model, we are also able to simulate and model the sort of balancing act of L1, your first language, and L2, and second language. And also with these type of models, later on, we were able to actually simulate language. Even though these two people speak the same language, actually you can see what these words mean to them are often very different. Education versus women versus business, they tend to be associated with the different words in their vocabulary. So models are really able to inform us of not just how the two languages in your head might be competing, but even for the same language, how they might be actually quite different. So more specifically, we have used these models to simulate age effects and the competition between the two languages. So we can train your first language for some time, and then we introduce the second language. And so we can slide this time window at the different points in order to see how your first language training is consolidated or not. before we introduce the second language. So this way would allow us to simulate the effect of age in a very controlled way. We can say, I want your L1 performance to reach some point before the second language is introduced. And then we can see even how your L1 performance might decrease because your L2 kind of takes over. Or we could actually continue training L1 and L2 to simulate a situation in which an older child has gone into a foreign country, but it keeps his or her native language. So these models are very flexible in this respect to allow us to simulate various scenarios. Without getting into the detail, some years ago we published this review paper to propose this sensory modal integration hypothesis to account for the age of acquisition effect in terms of neural and computational mechanisms. So to give you one example to illustrate what we mean, so we would train, in this case, English as the L1, Chinese as the L2, and then we can introduce Chinese at the various points in time. So roughly speaking, we can model the early stage of L2 learning and contrast it with the late stages of L2 learning, where you can see, given the same vocabulary, the same parameters of training, it's just the time difference. We could represent these two these L2 in different structures. Late learning tend to give you a representation that's more fragmented, disjointed, and less well-organized structure in the second language. So early L2 learning actually can lead to distinct representation for the two languages. So we could also, the other thing is that we could easily flip whether L1 is Chinese or L2 is Chinese. So in this case, for example, L2 is in English rather than Chinese. We really get very similar results in terms of the structures that you can see emerging out of these models. So within a late scenario, then you will see that the L2 tend to be fragmented, and more specifically, they tend to sort of be parasitic on the L2. So these words tend to take the established structures from the first language and then sort of map onto them. So, so parasitic representation is a very clear feature of late language learning rather than early language learning. So with the early language learning, for example, we could even see. So if you zoom in onto the second language, you can still see established categories in terms of nouns, verbs, adjectives coming out of this second language learning if it had occurred early on in your life. So just by way of illustration, I wanted to say that these models give us a lot of flexibility in modeling a variety of scenarios in the second language learning, alongside your first language learning. And recently, we wrote a short review article. Actually, it's not that short, but to illustrate how these models, various types of models, can inform us about the neurocognition of multiple languages. Angela and Jennifer are two grad students in my lab who just recently graduated. And there are some studies that they have performed I will get a chance to very quickly talk about. So we can understand the age effects or age of acquisition effects by studying dynamic reorganization and the competition between two or even more linguistic systems. Now, I think a very important theme running through this symposium has been that language learning or science learning in general is a dynamic process. And this is also the view that I take to study bilingualism and second language learning. So we wrote various articles, or we published various studies that illustrate second language learning from various aspects, whether it's a structural brain change, neuroplasticity, or this is actually an article that appeared, a very short public review article appeared in Penn journal a couple of years ago, 2 years ago. So the dynamic process is also what I wanted to share with you based on our work. So understanding second language learning from this dynamic view involves the studies that we have done in terms of age effects. I just very briefly mentioned to you, early versus late learning could result in different structures in the representation of the second language. In the next few slides, I will talk about some brain signatures of second language learning from both a functional and a structural change perspective. Then to study individual differences, we have been able to connect cognitive control, working memory, inhibition, and the like with the second language learning, both in terms of behavior and in terms of brain changes. And finally, one part of this, the final part of today's talk will focus on using cyber-enabled tools and compare language learning in these contexts with second language learning in the traditional context. And I think I will be able to link to some of the previous talks using virtual platforms, VR, and so on very well. So this is the plan for illustrating some of the studies that I and the colleagues have done over the last 10, 15, 20 years. Now, a basic paradigm in our work is to look at second language learning-induced brain changes. So in this approach, basically we would scan the participants twice, pre-training and post-training. Before you have been trained on a second language, and we scan you, and then after you've been trained to learn a new language, we scan you one more time. So time 1 and time 2. And then we can take the difference between time 1 and time 2 and identify which areas at the time 2 actually are more active as compared to time 1. And then we can start to make a story about which areas might be important for learning Chinese, Spanish, Swedish, and so on and so forth. So not only we can see quick changes in the brain after, let's say, 2 weeks, 3 weeks, 6 weeks in the functional aspects of the brain, but we can also study structural changes, such as gray matter increase, cortical thickness, and so on. So we could compare bilinguals with the monolinguals to see if, as a whole, as a group, do bilinguals actually have increased the gray matter density in some areas. So this graph illustrates that a set of key areas in the inferior frontal cortex, the parietal cortex, as well as some medial structures such as the anterior cingulate cortex, that's very much involved in language and cognitive control, and these areas actually undergo structural changes as a result of our day in, day out practice with our second language. So for example, we know the ACC, anterior cingulate cortex, is very important for things like conflict monitoring. So as I'm speaking to you right now, I have to clearly monitor my languages such that my Chinese doesn't get into the way when I'm speaking in English. And sometimes this proves to be very difficult. When I go to China, giving a talk like this to my Chinese colleagues, Chinese keeps sipping in and tries to interfere with my speech. So I have to use this area really extensively in order to make my speech fluent. And because of practice like this, actually this area experiences not just the functional changes, but also structural developments. So lately, we've also attempted to identify brain network patterns in order to study individual differences in a very important article published in Nature by 2 leading scientists, neuroscientists. They illustrated that we can take advantage of the typology, the distances and passes, and the community structures of these networks to understand individual differences in single areas, between 2 peoples, or in a group of areas that are connected, and whether they synchronize or they resemble one another within the individual and across individuals. So my student Angela Grant and I, along with several other students and colleagues, have explored this approach to see if actually second language learning success might be revealed by analyzing these networks of the brain. And so Angela, for example, performed a study with Spanish learning students at Penn State, students who have to sit in a Spanish class for a year or for 2 years. In this case, she tracked them over a course of 2 semesters, from the beginning stage to the more proficient stage. So she would present words like pie to Spanish students, to Spanish learners. So as you know, pie automatically activates the meaning of dessert for us. But in Spanish, do we have Spanish speakers here? In Spanish, it means something totally different. It means food. So as a first-time learner of Spanish, you just cannot inhibit your meaning of dessert whenever you see pie or PIE, the 3 letters. So in this study, we would put the subjects into the scanner, ask them to make decisions to words like PIE versus words like una, which is unambiguously Spanish. And you decide whether this word is a word in Spanish, not a word in English. So whenever you see PIE, you pause a bit because it's an English word that means pie, but you have to decide it's a Spanish word meaning food. But over time, when let's say if you have learned Spanish to such a degree that it's PIE, it's just automatic, it's food. Then you won't pause that much. So this is basically the idea behind our study. When you use these ambiguous words, ambiguous between 2 languages, in pointing to very different meanings, compared with unambiguous words in one language. Where we see differences in the response, as well as in the not just the reaction time, but also brain responses. So we constructed these network maps. So let's say I know those, as I illustrated, there are at least 5 areas that might be implicated in language control across languages. So we could construct how these areas might be connected at a given time, or we could construct the effective maps, which are time-lagged and can have directions. So unidirectional versus bidirectional maps can be done with the various algorithms. And in this particular study, Angela was able to track the changes in these networks from time 1 to time 2 to see whether some key areas actually, the flow of information actually changes, whether connections, you gain more connections between some areas or lose some connections. So at the time 2, for example, IFG and MTG gain more connections, indicating that the subject have been able to access semantic representations or meanings of these words more automatically. Whereas MFG and codec, these areas we know are implicated in cognitive control for 2 languages. And these start to lose some connections at the time too. So you need less control as you become more proficient in the second language. So these kinds of maps or networks are able to inform some changes in the brain as we become more proficient in the second language. Pankaj. These are cross-correlation functional along the functional time series. Yeah, these are not DTI maps. We could do this with the DTI data as well, with similar kind of algorithms. Yeah, but for this particular study, it's functional data, functional time series, both signals. We've also recently, this is a very recent paper that's actually this online, but it hasn't been formally published in neuropsychology, where we also compare the high versus low proficiency and see if the subjects actually in the resting state situation. So we just scan them when they are lying in the scanner, thinking of nothing, but don't sleep. We could see that high proficiency and low proficiency speakers, second language learners, in this case Chinese, we compare the high proficiency with against the low proficiency, we see decreased resting state connectivity from key areas such as ACC I mentioned, and MFG, and these key areas of control, and how they connect to other key areas in the brain, in the left, and sometimes to the right, that these two groups actually show different degrees of resting state connectivity for key areas involved in switching and inhibition. And these patterns also correlate very well with the performance scores. For example, this is a performance score with the inhibition, and these are the correlations with the performance in switching or flexibility. So actually, I switched. So A is switching performance, B is inhibition. So let me take a sip of water as Mark Zuckerberg. Since we have a little bit of time, let me actually see if I can show you this video. Mark Zuckerberg is an avid Chinese learner.
我太太是中文。他家说中文和他的奶奶只说中文，所以我想要跟他们说话。
So Mark Zuckerberg's Chinese is pretty good. It's pretty fluent. For the non-Chinese speakers in this room, what do you think his main trouble has been? Just the tones, yeah. His Chinese tones are off by quite a bit, even though he's fluent. So native speakers, you will automatically or very quickly detect that he has trouble with the Chinese lexical tones. So study we did a few years ago, we actually trained American students learn Chinese tones, and this particular study, led by my former postdoc, Jing Yang, illustrated that we can actually detect the successful learners and identify their brain network patterns from the less successful learners. So with the successful learners, you will see the superior temporal gyrus, a key area in phonetic detection, as we know from many monolingual native speakers studies, that this area is the key for understanding Chinese lexical tones, and it connects very well to other areas in our study as well for the successful learners. And when we compare this with the less successful learners, that we can see less successful learners have a very less connected network, and almost no fundamentally different from the control learners. These are the learners who actually have not been trained on Chinese within the 6-week period. So what also surprised us in this particular study was that not only at the time 2, when they have been trained for 6 weeks, we see differences between these three groups, but even at time 1, now time 1 is a time when they have been trained just for 1 week, because we wanted them to at least be able to respond to the task. So with at the time 1, these people have already established a sort of multi-pass network that prepared them to really progress and succeed in language like Chinese. So our work really actually indicates that these networks in the brain can even not only to allow us to identify different individual groups, but also allow us to predict future success down the road. So then we also did a study analysis to look at the activities in some key areas for language control and learning success, and whether these correlations would relate to other nonverbal intelligence scores, reasoning, and control scores. So we see these kinds of 3-way brain, behavior, and cognition correspondences. So that's what I meant to tell you or share with you about the first two aspects of the learning studies that we have performed in the case of second language. So learning is computational, you got a sense, and learning is brain-based. And in the last part of my talk today, I will focus on the idea that learning is based on social interaction. This is no new idea. All of us, in fact, in the previous talks in the last 2 days, we have seen plenty of this. So how do we see that in second language? Okay, before I talk about the second language, some of you might have heard about Deb Roy, who installed cameras in his house and recorded his child 24/7 for a year or so. And from these videos, some of which are online, you can see that the kid is just constantly moving around, from day one, when the child is able to crawl and move around the house. So it's a very interactive process in the case of child language learning, as you might have heard from Linda's talk the other day, that the child really needs to be in the situation, moving objects, manipulating objects. Now, compare this with the second language learning situation. So my wife is a second language teacher. She stands there, give students drills in Chinese, tell them about keywords and key grammar patterns. So students are sitting, learning these associations, in these classrooms. So second language learning is very different from first language learning. So if you are, for example, if you are a kid going to the zoo, learning about the animals, the kid would, baby Bob, and would ask Barney, what's that, what's this? And basically building up a big correlation matrix of features and names. And these correlations might be implicit, so the kid is really doing statistical learning in some cases to identify the size, the shape, and the movement patterns of these animals. So going to the zoo, seeing the animals, sometimes even can pat on them. Now, in the classroom learning situation, we are learning about these animals. The teacher says, 乌龟 means turtle in English. If you're learning Chinese, 公鸡 means rooster. So you make these associations. Sometimes maybe aided with a picture that helps you to remember. So that's how classroom-based, translation-based association learning occurs in the classroom. That's what my wife would do. All of the second language teachers would do, at least in the classroom at the beginning stages. Now we know that the first language or native language representation is not like that. We would activate perceptual sensory systems in all of these modality-specific areas of the brain once we learned or acquired a native language from the context. We use auditory, visual, olfactory, somatosensory, and motor cortex to engage in the process of language learning. In addition to using more abstract anterior temporal systems. So according to the hub and the spoke model of semantic cognition of Lambaroff and colleagues, this is how in the native language representation situation we would do by engaging both modality-specific and modality-general systems for representing meanings and concepts. According to predominant theories of bilingualism, so for example, my colleague Julie Kroll and Hernandez, these models indicate if we have learned a second language through the traditional classroom-based approach of making these L1, L2 associations, gongji, rooster type of thing, you tend to, every time you see this L2 word or hear the L2 word, you tend to just automatically activate your first language and then go to the concepts. So you learn to toga, you just, almost impossible for you to inhibit the native language word total, like what we've shown in the earlier case of pi. You activate forced language, and then from the forced language, you go to the concept. And what we need to do is to build up this direct connection between tautology and the concept. And we often are unable to do so because of the way we have learned our second language. So, in some cases, it could be even worse because when we look at languages like Chinese as a second language, it's very different from English. So, for example, if I was a first-time learner of English, I would look up the dictionary for the word tiptoe, which says you walk with your heels raised up. Okay, so I have to kind of figure out what that means exactly, and because in Chinese, there is no single word that corresponds to tiptoe. So the best way maybe, your teacher actually will walk in the classroom with the tiptoeing to show you what that really means exactly. So we have, so this last part of my talk is to say, can we actually find a way to teach second language more like the child learns for a first language? So can we actually allow the learner to break away from the first language system? Earlier in our computational model, I showed you in the late learning situation, actually your second language tends to be parasitic on your first language. Can we actually find a way so that your learning actually already breaks that away, parasitism away? In education, as many of you know from some of the talks yesterday, the situated learning is a big thing right now because it enables the interaction between the learner and the learning environment. It allows modality-specific systems or experiences to be engaged. In cognitive psychology, we have this big theory of embodied cognition. In a recent review paper by Johnson Glenberg, she talked about affordances and agency. Affordances of these objects and properties in the environment, and agency, the ability that you actually can perform activities, can manipulate objects in virtual reality systems. And Johnson Glenberg was interested in how virtual reality could help students learn chemistry, math, and the like. And just last night, I was sitting with the two memory researchers from Lund. I was thinking about how episodic memory becomes semantic memory. And through repeated exposure and episodes, you actually change episodic memory into semantic memory. When we learn a second language, we don't have that process. We just translate or convert our second language label to our native language. We totally get rid of these episodic experiences with the different types of dogs, different situations in which the dog appears, and then build up the concept of dog. So these situations speak to some fundamental differences between second language learning and first language learning. So having those ideas in mind, over the last couple of years, we built some virtual reality situations, scenarios, such as virtual zoo, virtual supermarket, virtual kitchen. And we constructed some of these environments on a platform called Second Life. And we trained American students to learn foreign languages, in this case Chinese, in these virtual environments, so that you can build your own avatar and move into these environments and walk around, look at the objects, and move them across different places. You can move the animals, but you can see the animals in different perspectives. You can come to one animal and then go to learn another animal. So you have a lot of freedom in doing this. I hope I have a little bit of time to give you very quick demos of some of these contexts we have built. So in this study with a visitor and 2 students in my lab, we actually compared virtual environments learning a second language vocabulary in this environment with picture word associations or word-word associations. Same amount of time, same amount of training sessions, and with same kind of protocol of scanning before and after. And we also run cognitive testing before and after. And the students would learn 3 categories, 30 words each in each of these virtual platforms, and 5-minute learning session in each session of learning. So this graph very quickly illustrates that the picture word association learners, as compared with the virtual environment learners, actually are better off at the earlier stages, because they don't really have to get familiar with the virtual reality environment at all. But by about 5 or 6 sessions of training, they start to become very similar. So in other words, the VE learners don't really do well at the beginning, but they can catch up quickly later on. What this graph also doesn't indicate to you is that the VE, the virtual learners, actually have have only half of the time of number of trials as the association learners, because in the virtual environment, you actually have to pick up or tap an object in order to hear it, whereas the association learners just press the computer spacebar and hear the association over and over again. And then we also scan these people and give them tests, at time 1, which is the time when they've just got a few exposures, one trial, one training session, a few exposures, and then we ask them to make a decision to 4 pictures when they hear a foreign language word. And in these, when we compare the virtual learning and association learning cases, at the time 1, there's no difference. At the time 2, however, we see significantly more errors that become active in the virtual learning situation. For example, errors such as superior frontal gyrus, middle temporal gyrus, the caudate. These are the errors that are involved in, for example, spatial memory, semantic access, and the sequence learning. And that makes sense that we see only activities in these areas for these activities in these areas for only the virtual learners. Not only we see functional changes, we also see structural brain changes over time. So this was a student, Jennifer Legault, who found that the virtual learning situation, so the virtual learners see more, with the virtual learners we see more of the right IPL changes, whereas the non-VR learners, we identify more left IFG changes in the brain. And there's a reason why these 2 areas are dissociated structurally, which I won't have time to really get into. In gray matter volume analysis, we also see some of the key areas that experience change as a function of learning new language, and probably as a function of bilingual cognitive control in these cases. For example, working memory is one area we can see. We can correlate working memory scores or working memory performance of these 2 types of learners with the structural brain changes at the key areas in the left caudate and the right supramarginal gyrus. And it's only the virtual learners where these correlations are significant. Why? Probably because the virtual learners need to engage the working memory much more so than in the association learning case where the learner just presses the spacebar. And the virtual learners actually has to keep track of what is being learned and in a very highly demanding situation. So let me see if I can actually show you a very quick demo in which the student is learning. So the rooster, you hear no native language. This is only second language. So we are hoping.
松鼠
We are hoping that this type of learning somehow, get rid of your first language, doesn't involve your first language in the case of learning a second language. So with the colleagues in statistics and human development for the team break, we will develop some tools to analyze these data. For example, if you are walking around in the zoo, you can go to learn the rooster first and then the fox, but you have the total freedom to move back and forth. So let's say if you have 4 objects to learn or 4 animals to learn, you can just follow a fixed pattern from one place to the next, just run in loops, for example. And in this case, we have the so-called low roaming entropy, and with high certainty to predict where you are going to go next. Or learners who, given the same 4 animals, they are actually kind of roaming around. They don't know which animal they are learning. So if you just look at the trajectories of movement, you have very low certainty to predict where they are going to go next. But it turns out it's the students who seem to be roaming around who learn better than the people who do a fixed route. They just, I learned rooster, and then I go to the next, and then I go to the next. So the high roaming entropy students tend to actually learn better because they are the ones that are exploring. They hear a sound, rooster, that may be sounding similar to another word that they learned before. Then they go back and compare these two. That's why you end up with this so-called high roaming entropy. So these methods allow us to incidentally or non-incidentally, so this is a postdoc in my lab, we try to see the high achievers or the better learners from the poor learners, whether they have some strategy differences. So the better learners tend to use the so-called cluster strategy, where they look at the objects' spatial features, appearances, and functions. So they cast the objects based on how they are similar. So let's say I'm learning table and chair, even if they are not next to one another. Whereas the students who use this so-called nearest neighbor strategy, these are the ones that actually tend to learn much worse. And we could analyze how they group these animals and objects in the virtual environment. So this is one way where we don't have the flexibility with traditional association learning models. So more recently, we have been able to build more immersive and interactive virtual environments with a professor in geography who is interested in spatial cognition. So we would have subjects wear a pair of goggles and immerse himself or herself in these virtual environments. So seeing the pandas and going into the kitchen and moving objects. I have a few YouTube videos on the website if you guys wanted to take a look at them later on. But here's one very quick demo of how the students are learning in the virtual animal zoo or the animal island. So you wear the goggles.
螃蟹
So you have 2 pairs of remote control. One points to the animal,
乌龟
and then it
乌龟
will activate the second language. Another pair of remote control, you can advance yourself through the path,
小鸟
through the island.
小鸟
So this is one scenario where you actually can be immersed in the environment. Another case is the kitchen. So in this time,
饭碗
in this
餐
environment.
桌
So on the right-hand side, you see actually this is the VR lab. This is my daughter learning Chinese by just moving around in this
漏
lab.
斗
But this is what she will see in the virtual kitchen. She can pick up objects.
剪刀
and move them. So she's left-handed. So in this case, she actually uses only just one. You only need one pair of remote control to move objects. You can walk around without the other remote control to advance yourself. So move objects around, hear the sound, interact with them. She also repeats the sound that she
烤
hears.
箱，烤箱，
She can even open the oven and close it. Very, very interactive. And now watch, she's going to pick up the broom because it dropped on the floor. And she kneels down, picked up. So these are the kinds of interactions that we would
钢
imagine
杯，钢
that the child would have
碗
when learning a first
餐
language.
桌，
But something that the second language learners sitting in the classroom really don't have. So this is also a freshly published article where we use the immersive virtual reality to train second language vocabulary learning. And we compared, so overall, the immersive VR works better than the word-to-word association learning. But also there's a difference in terms of whether you are learning in the kitchen environment or the zoo environment. And tentatively, we were thinking that in the kitchen scenario, you have more interactivity in the situation of learning. You can actually move objects, manipulate them, and so on. Something that you don't have in the zoo, where you actually just use a pointer to the animals. But also, again, surprisingly, that we didn't expect was that for the two types of learners, the successful learners, we see whether it's VR or associative learning, it doesn't make much difference. Whereas for the people who are struggling, I think the struggling was the word that Johan used. For these less successful learners, VR really helps a lot than the association-based learners. So maybe it's the case that we don't need the technology all the time. For some people who are good learners anyways, it doesn't really matter that much. But for the people who are less well or who are less successful, the technology effect can show more clearly. So it's like, for some part of the population at the top of the pyramid, it really doesn't matter that much. And the technology effects will be working best for lower part of the pyramid groups. So this is just a tentative hypothesis of how we might see these effects of technology. So quickly wrap up, VR, virtual reality actually provides a very unique opportunity for us to study real-world experiences in the lab because of the design flexibilities of simulating real-world environments. While having tight experimental control. So some colleagues at Penn State are actually trying to see if we can build virtual reality workshops and compare with the real engineering workshops to, in this case, you also don't have the risk of cutting your hands when you are doing some sawing experiment. But we can compare the effectiveness of learning across these platforms. Now, these VR environments also enable us to collect a very large-scale continuous motion, haptic, eye movement, and even neuroimaging data. So, for example, Toby developed this system that allows the recording of eye movement and eye fixation data. And there's a company that actually has developed EEG system integrated with the VR. So these technologies really allow us enable us to do very large-scale data collection and analysis. So very quick summary, neuroplasticity in the second language learning situation, as I mentioned earlier, reflects the effect of timing, age, the nature of the learning task, and the extent, so how much effort you have spent, how proficient you have become in the learning process. And we can study individual differences by looking at data-intensive computational models and methods and brain network analysis. And the cyber-enabled methods and tools allow us to study both behavioral and brain changes. It provides a new synergy for us to connect cognitive neuroscience with the technology and big data analytics. There are some open questions that we hope that we can address together with many colleagues. How can we best study multimodal situated learning in naturalistic context so that we can manipulate the ecosystem of learning to identify specific types of experiences and how these experiences might lead to specific expertise. And finally, how can we translate the basic scientific results from works that you do, studies like we do here, to the design of programs that can better student learning. So to address this last question, let me give you one example. This is totally an outreach project that we've done. Traditionally, learning the structure of the brain or neural anatomy involves coloring picture books like this. And lately, we've developed interfaces that enable students, especially middle school students, to learn about the brain through 3D interfaces. And this is a 3D interface that we developed in our lab, which is actually available on the website, so that the students can actually, rotate the brain, tone the brain in 360 degrees, blow it up, or click on specific areas and see further explanations of these. So this type of learning has been preferred by especially middle school students than the picture book-based coloring type of learning. So this just illustrates how the students is moving around in our 3D interface. And most recently, we have been also interested in whether spatial ability actually can modulate some of the anatomy learning differences. Students who are better learners than poor learners, as compared to students who learn very poorly in these cases, learning neural anatomy. And finally, we've developed a virtual reality immersive context for learning anatomy. And here's one case where the students will get into the environment. Actually, I'm not able to show you this. Maybe let's see if I can pull up this videotape to show you. There's a So here's one example where our virtual environment for anatomy learning So the student actually goes to the table, opens up the brain, and you can rotate the table to see different parts of the brain structures. You can point to certain areas in the brain and see the labels. We are also implementing the sound, not shown in this video. And you can take up a part in the brain and see this in 3D, move it to the template, the other template, to fit into the specific area in the brain. If it doesn't fit, it pops out. So this is just one example of how we are trying to make learning to be more interesting for the students. Let me see. Let me go back to my final slide. So the overall approach we have, I hope I have illustrated for you is that we are trying to connect the learning with the brain changes, functional and structural, using technology and making use of big data analytics and the models. so that we can better understand the learners and the individual differences, and eventually hoping to transform education. So there are some future promises in terms of this approach. I think data over the next, yesterday we had a discussion of what does the future look like down 5 years, 10 years, and so on. I think a data-intensive and technology-driven analysis of both brain and behavior in real and simulated environments, it really holds the promise for understanding individual differences in first language learning, second language learning, and even learning in general. And the methodologies you will see with the rapid developments in methodology in the industry, it allows us to collect and analyze very large-scale, multimodal, continuous real-time data from variables, immersive VR, and other imaging tools, and combine the tools to study human-technology interaction and learning effectiveness. So I think these are some of the directions that I'm really excited about. So finally, I wanted to thank the National Science Foundation for providing a lot of support to our studies that I quickly gone through here with you. And I really haven't got time to talk about the recent project based on the Brain Initiative. I only wanted to mention that we have on our website, there's a website called Reading Brain. Feel free to see some of the videos and the demos. And we've collected a huge amount of data with that project to study science text reading and the brain changes that occur with these reading processes. So we have so far collected over 160 participants in the scanner with over 200 gigabytes of raw data. It's multimodal brain imaging data with the cognitive behavioral testing and eye movement data. And it is just uploaded to Open Neural last week. And anybody can go to Open Neural, download our Reading Brain project. So far, this is so far only the 4 native language adult readers, and we have over 50 subjects in these data sets. And we are hoping to post the L2 adults and L1 kids over the next couple of months. So with that, I want to thank all the collaborators and the postdoc and students who did a lot of the groundwork, and thank you for your attention.
Thank you very much, Ping Li. Right. Actually, if you have questions for Ping Li, your questions go first. After that, I might have some. Yes. Sorry, I threw it a little. I didn't want to hit the camera.
Sorry, I just want to know what do you mean with late and early learning? So how fixed has the first language to be, or how stable? And what do you mean with early and late?
So the way I see early and late is really on a continuous scale, on a continuum. There's no, unlike the hypothesis from things like a critical period and a sensitive period, where they tend to have a cutoff point of, let's say, age 12 or 13 or puberty. I don't see a very sharp boundary for early versus late. In our models, of course, we could easily manipulate. Let's say I could train the first language up to all of the vocabulary has been learned to a criterion, and then introduce the second language. That's the sort of latest case. Or I could interject the second language into a somewhat earlier stage or very early stage where the 2 languages are learned simultaneously. So really, there's no absolute boundary to define early and late. And I didn't mention specifically that one view to see the fundamental difference between first language and second language learning is that in the second language learning case, it is very often the situation that we have already established a first language to some degree before we learn a second language. And that, whether it's interference or entrenchment from your first language, is going to be a major factor to the process of our second language learning, and it could affect effectiveness, speed, and eventual outcome.
Thank you. I was curious. Yes, I'll pass it on to Marianne, but I was thinking of something that ties in a little bit to that, I think. Do we know anything about how many languages can sort of occupy this first language space? Children learning 2 languages simultaneously, that is pretty common. 3 is a little bit more uncommon, but that does happen. Do we know how many we can sort of fit in on that first position?
We don't know. Actually, I don't know if anybody has studied the issue, or whether it makes sense to study the issue, whether we have a capacity for the total number of languages we can learn from the early time or early stages. I can give you one example. For example, my wife grew up in Malaysia, and she basically acquired Malay and English as a kid. And then Malaysia was a British colony for a long time, so English is also a formal language. And then at home, her parents spoke 2 dialects of Chinese, which are mutually unintelligible. So the parents would speak each of their own language with my wife. But the parents themselves communicated in Mandarin. So there are 3 languages going on in the household, which she all acquired to native proficiency. And then she learned Spanish and Japanese. So she has basically 7 active languages with her. And they all seem to work very well for her.
They seem to be. Do they all seem to be on first language level?
At least 5 of those are first language level. So. So I really don't know if there is a limit as to how many languages you can learn. I mean, there might be, if you really want to quantify it, I think there might be a period of confusion or interference or mixing up, depending on the degree, the number of languages you have. Whether you get a constant interference and confusion in the usage. Yep. But other than that. I don't know how we could specifically quantify or put the limit, put a cap on the number of languages you can learn. From early on.
Right, thank you. Right, okay. Oh, you got it. Super. You did it all by yourselves. I'm so happy, thank you.
3 days later, we've learned the game. So now I'm just tempted to tag onto your question, but I won't. I'll ask my intended question to P. Lee. It's a really impressive body of work, and it's very intriguing to see the VR work with this kind of temptation of creating something that is slightly more ecologically valid than a typical foreign language classroom. One thing that is strikingly missing, though, from the VR environments is something that would generate production on the part of the language learner. Because again, if you want to make the comparison to children, obviously what children do is not only listen passively, even if they don't say very much, perhaps for the first 9, 10, 11 months, at some point they will actually start producing language. So a question is whether, A, you are thinking about introducing the learner production into your VR studies, and secondly, whether and if so, what do you think might be the problem with that? Obviously, I asked the question because I have a suspicion, but it'd be interesting to hear your take on this.
It's a very good question. When I showed that video where my daughter was moving around in the virtual kitchen, you can see that she actually repeats some of the words to herself. So I totally agree with you that we need a production. The kids learning language, they involve both comprehension and production. It's just in this environment, for experimental purposes, we wanted to put a tight control over the comprehension aspect, and so that we can record everything in terms of the learning success and performance. But I think the technology is there. You can enable production performance in the VR. You can record them. The question comes to what issue you want to ask with this platform, and how you want to design your experiments. So I think it's totally doable. I think yesterday Dr. Hamilton also showed a simplified VR case where you have a projection onto the screen. So this side of the subject would actually be interacting with the interlocutor, who is virtual. And this type of interactive conversation or conversational partnerships could definitely be implemented in the system with the technology. And there's a lot, there's a million of things you can do with this technology for both research and practical teaching, learning considerations. Yeah.
Can I just come back very quickly? And one of the reasons, a practical reason for asking the question is, psycholinguistic experimentation on production is much harder than comprehension, of course, because people can say whatever they want, right? You don't have the same control. But a second issue is, of course, as you said, what do you do with a production? You need to code it for accuracy and pronunciation accuracy and so on. And the theoretically interesting question connected to that is that there are theories concerning learning that suggest that if your production isn't quite what it should be, then you might be creating an extra entrenchment of some sort of representation that isn't accurate, making further learning slightly more difficult than if you hadn't said anything. And again, the comparison to first language acquisition is that children are silent for a year before they actually start saying anything. And when they open their mouth, they may have a better chance of producing something that is, let's call it target-like, than a second language acquisition person who tries to speak after 5 seconds. So, there are all sorts of reasons why production is both complicated and interesting, but I think it would be well worth trying to implement something like that into these VR models.
Yeah.
Also, because, quite frankly, when people like our excellent moderator ask, how many languages can you learn, or what do you know? People in general, they think about how can you speak, right? Production is somehow the defining criterion of acquisition to most people outside of this group, right? So again, another reason for why that's an interesting thing to do.
Yeah, I totally agree. I think
shut up now.
There's also, even in the case of child language, we also see, a great variation in terms of, how long the child actually hold off before saying a lot of things all of a sudden. From parents' experience, we also have that some of the kids just, they are brave and they just keep throwing words at you. But the other kids will, be having the complete comprehension stage for a long time before they come out totally fluent. So how we can study these kinds of processes in the second language case with the VR technology, I think that's a really interesting issue to think about.
Thanks. Yes.
So I have quite a different question. I was interested to see that second language learning is associated with increased grey matter in certain regions of the brain. Now I'm thinking that aging is associated with decreased grey matter, and age-related pathologies like hearing loss and, of course, even more dementia are associated with even more grey matter loss in the brain. And I was wondering what you would think about second language learning as a therapy to stop or reverse these kinds of effects.
Yeah, so in terms of the effect that second language brings to the brain, there has been in the last decade a lot of debates and discussions. We have Johan from Lund, who has done really pioneering work in terms of understanding the structural changes in the brain as a function of second language experience, especially like interpreting and so on. But so there's, I'm sure some of you may be aware of Alan Bialystek's theory about how bilingualism might actually delay the onset of neurodegenerative disease. And her theory has been that even though there might be gray matter decrease in the aging population, the structural integrity and some of the structural connectivities remain to be there. So second language may have acted as a protective mechanism to healthy aging. So that has been the argument from Bialystok and Jubin Abutalebi and a few other colleagues. I think lately some of the data have been conflicting, to say the least. Others haven't found clear evidence for not only for the younger population where our cognitive performance has been at the peak, but even for younger children and late adults or aging population, whether these effects exist across the spectrum, and whether we can really talk about this bilingual advantage as a whole. I think even Bialystok herself has presented a more fine-grained proposal rather than just saying there is a bilingual advantage. I think she and the colleagues, many colleagues realize that we need to look at the specific groups of people. There's a huge individual variation across anybody, any spectrum. And also, we need to look at the specific cognitive control components. Well, is it switching? Is it inhibition? Is it updating or working memory? Is it the monitoring? These different components might be implicated differently in the case of bilingual abilities. So the story has become quite complicated in the last couple of years with some results from some studies. So the issue regarding bilingualism as a protective mechanism for aging, I think is also being carefully examined, if not being put on hold. That's my understanding currently. A lot of work remains to be done in this regard to really sort out to the effect and the degree to which bilingualism can actually lead to healthy aging.
Okay, thank you.
Yeah, so I think the rationale for the VR, as you took us through the rationale, was that you have argued that it would be better to encourage these L2 learners to learn as if they're learning an L1. I think that's essentially the rationale. So that's quite a big assumption to assume that we can get these L2 learners to learn as if it's an L in the same way as an L1, even once they've established a robust first language. So there's all kinds of questions around that, especially from the world of deafness, where we have kids who come to learn sign language late in life, but on the basis of very impoverished L1 in some cases, and they really struggle. And there's all those issues around that. But let's assume that what you're saying is correct. To really test that hypothesis, I think that your VR comparison with the picture word matching is perhaps not yet the best comparison, because the VR environment is incredibly rich, and if you had a much tighter control where in that VR environment, things were visually labeled with the English, with the L1 word, as well as them hearing the other. I know it's not what you want to do, but that would really test your hypothesis about this moving away from, I'm not sure what phrase you used, but trying to go directly from the L2 word to the concept rather than via, what word did you use? Parasitic, rather than this parasitic route. And I wonder, in that very strict contrast, either when they heard the L1 word and the L2 word versus just the L2 word, whether you actually still think you would see differences, especially in these poorer learners.
I think this is a very good question in terms of whether we can directly compare the VR situation with the sort of association-based contexts. The contexts themselves are very different. As you pointed out, VR entails a much richer context and the cues and other things. To make the matter even more complicated, people might be having different motivation in these two contexts. In the association-based learning, it's just boring. You're just making this. Whereas in the VR, you can, in a way, more interested in the environment. So how to really directly compare them? I think that's a very interesting question. One thing that we have thought about this in this regard is to really provide the same sort of enriched environment, but different ways of presenting. So for example, if I want to really say, is it really interactivity that led to better learning outcomes? So I can present you with a 3D movie, like, with this VR, but having you just sit there and not interacting with this environment. So this is one way where you can follow another person's learning trajectory. Does that help you? So let's say, rather than actually manipulating the objects, you see somebody else doing the manipulation. You are given exactly the same context and the cues and learning targets. So does that make a difference? So that would be able to allow us to see the effect of specific components, such as interactivity. But in other cases, you can, for example, reduce the richness of the context. So I can just make a interactive context like the association-based, let's say, line drawings, cartoons, but allow you to be able to move around and so on and so forth. So there are various ways in which we can try to really make them comparable, so to speak.
But I think you're right, but I think they're all questions about VR environment and context. Whereas if you really wanted to test that issue of trying to break the parasitic link with an L1, then you could keep exactly the same environment, but when they go to touch the kettle, they have it in L1 and L2, but your hypothesis would be that they would learn better when they only have it in L2.
Yes, one hypothesis is that when they're actually touching the kettle, they hear the sound of the kettle in English. If I were to learn English, then the hope or the assumption, one of the possible assumptions is that the first language isn't directly active in the context of learning. And we could test this maybe with other methods in the future to see if you learn this way versus another way or association way. At a later point, when I test you, is your first language similarly active? So there has been a lot of studies indicating people who are seeing the second language label or word, their first language automatically become activated. So this is the idea of parallel activation. Now, if you have learned, when you learn the second language label without mediation of your first language, does that give you lower level of activation of your first language? That's something that could be empirically tested, maybe at the various stages, I think, to address your question.
Thank you.
Thank you. And thank you very much for being here at the conference, for the interesting presentation, and for the generous session here today. So thanks, Professor Ping Li.
Thanks.